right, so what is your question?
It's about problem 2, explain why transverse cone drives experience pull effects, why longitudinal cone drives do not. It's just, it wasn't immediately clicking with me. I think in the notes, I have something to the effect of, in the case of transverse cone drive, the electrostatic force is not dependent on position, as did the gaps between the buses.
So for longitudinal cone drive, let me draw a picture here. And I think this will likely make things close out all these windows for me talking about electric motor stuffs. And then circuits 1 exams. So the question that was posed is one of the questions that I posted on the review thing. Why do transverse cone drives suffer from or experience a pull-in effect while longitudinal cone drives do not, right? So in a transverse cone drive configuration, let's say that these are a set of stationary fingers, and then here in the center is our movable finger. So in a transverse configuration, our movable finger is moving from left to right. And so we see that this distance between our capacitor plates is what's changing, right? And the pull-in effect occurs when we have parallel plates and one of them is moving towards the other. In a longitudinal cone drive, though, we have the following situation. Where our direction of plate movement is like so. So the gap between the plates doesn't change. And so the pull-in effect can't have any, it doesn't occur because the gap is remaining constant. Does that make sense?
It does. I think what was in my mind is that if you allow the cone fingers to go close enough together in a lateral or longitudinal configuration, you can get a pull-in effect from opposite sides. And that's what I was thinking.
Like you could get, so you're saying like,
if it goes far enough towards the opposite side, there's a parallel area there, you get some fringing capacity.
yeah, so, okay, so that's very fair. That being said, the areas that you're dealing with there are very small. So you would absolutely have the potential for a pull-in effect, but the force that you're going to generate would require an incredible amount of, or the force that would be required would require an incredible amount of voltage because of the small area, because you would be seeing a pull-in effect from just this single surface of your finger, right?
So not that there isn't one, it's just negligible.
Effectively, yes. So I mean, you're 100% right that the fringe capacitance there is going to potentially have some type of pull-in effect if we were to move that finger close enough to this sidewall portion. But it would require a large voltage to actually cause pull-in because of the small area. And generally speaking, like while we do get a relatively large movement in a let's see, so now I'm trying to think of which one. Longitudinal cone drive configuration like this, increasing the area of the plates, probably not going to actuate it so far that it comes close to touching that edge, right? Because the gap between these fingers is typically on the order of a few microns, right? To minimize the fringing field, this gap is usually on the order of tens of microns or more, right? So we would have to induce an extremely large movement in order to get those to be in a place where a pull-in effect would occur.
Thank you.
Yep. All right. So we are going to be talking about both longitudinal and transverse comb drives today, because we're going to be working on a problem involving a gyroscope that uses a longitudinal comb drive to provide actuation and a transverse comb drive to sense the effects of a Coriolis force. So before we talk about that, though, one thing that I want to bring up is that in all of our capacitive actuation schemes that we've talked about previously in this class, DC voltages are utilized. So let's talk about what happens when some combination of DC and AC voltages are used. Effectively, how are we going to get an oscillating force to drive our vibrator, right? Or our resonator. So we know that the electrostatic force, Fe, is the derivative of the energy with respect to position. And for a capacitor, this is going to look like 1/2 the derivative of the capacitance, where we're assuming that we have a movable capacitance or a changing capacitance, which is exactly what we have in our MEMS situations where we're undergoing capacitive actuation, times our applied voltage squared. So let's say that V in this case is some DC voltage plus some sinusoidally oscillating AC voltage. So a combination of these two voltages, and then from here we can cover effectively every possible configuration, only DC, only AC, and combinations thereof. Our electrostatic force, Fe, will be 1/2 times our voltage squared. So that's going to be VDC plus VAC cosine omega t, quantity squared, times our change in capacitance. And if we go ahead and expand out what we have here, we're going to have a term of VDC quantity squared. Then we're going to have our cross term, right? So that's going to be VDC times VAC cosine blah, blah, blah. That's going to occur twice. So twice VDC, VAC cosine omega t. And then we're going to have our AC term squared. Well, to get our AC term squared, we're going to have to use a trig identity here. I'm going to write it in blue really quickly. So if I have A cosine angle 1 times B cosine angle 2, this is going to look like A times B over 2 times the cosine of angle 1 minus angle 2 plus the cosine of angle 1 plus angle 2. So it's just half the product of the magnitudes times the cosine of the difference in the angles plus the cosine of the sum of the angles. Well, in this case, our magnitude is VAC. So we're going to have 1/2 VAC squared times the cosine of the difference. Well, the angle is the same, right? Cosine omega, we're having omega t minus omega t, cosine of 0 is 1. So we get another DC term here effectively from the AC term. And then we're also going to have 1/2 VAC squared cosine twice omega t. So we're going to have a sinusoidal portion that's oscillating at twice our angular frequency of excitation times our change in capacitance with respect to position. So this is our generic form. There are a few special cases that we are going to look at because they apply to gyroscopes. The first option is if our DC applied voltage is much greater in magnitude than our AC applied voltage. So effectively, what that's going to do is it's going to make that twice omega high frequency term go away, right? Because we're squaring the smallest possible thing, right? So in this case, our electrostatic force is going to look like 1/2 VDC squared plus 1/2 VAC squared. I'm leaving this term in because it's going to combine with the DC portion to create a DC offset for the system. Plus twice VDC VAC cosine omega t times DC by dx. And I'm going to expand this out a little bit more. So 1/2 VDC squared plus 1/4 VAC squared times our change in capacitance plus VDC VAC cosine omega t by our change in capacitance. I'm putting it in this form in particular so that we can see that there is going to be some DC component of the force, and there is going to be some sinusoidally oscillating AC component of our force that we could utilize to cause a structure to vibrate. For a DC term that is 0, meaning we are only using an AC term to drive our system, our electrostatic force would simply be 1/2 times the 1/2 VAC square term plus 1/2 VAC squared cosine twice omega t times our change in capacitance, and breaking this up into its constituent DC and AC parts, we have 1/4 VAC squared plus 1/4 VAC squared times cosine of twice omega t. Actually, sorry, I forgot the DC by dx term over here. My apologies. Once again, we have a DC component of our electrostatic force and an AC component of our electrostatic force. All right, so let's take this and let's look at a gyroscope.
How we are saying that the VAC square term is having the DC component?
I'm sorry, what?
How we are saying that the VAC component, the left part is having the DC component?
So it's from that trig identity. When we multiply two cosine functions together, we get a a part that is corresponding to a cosine of the difference of the angles and a part that's corresponding to a cosine of the sum of the angles. Well, when we're squaring the same signal, we wind up getting a DC term plus an AC term, right? So let me draw a picture and hopefully it'll make sense, right? So if I look at this is time. So if I looked at cosine, and I was able to draw a sinusoid to save my life, I would have something like this, but drawn less crappily, right? Well, if I square this thing point by point, what I'm going to wind up having is this. Something like that, where I have an oscillation at twice the frequency with some DC offset. That DC offset is what's being represented by this term.
Kind of like a replication.
Yeah, I'm gonna disagree there, because how I view rectification is I'm either suppressing my negative half cycle or I'm changing my negative half cycle to be positive. Whereas this is more of a function of so how I talk about this to my Circuits 1 students is when we're talking about the concept of instantaneous and average power in a steady state sinusoidal system, right? So maybe this will make a little bit of sense to you guys, right? So like intuitively, you would think that the average power in a steady state sinusoidal system would be the average value of the voltage times the average value of the current. But that can't be true, because the average value of the voltage in a steady state sinusoidal system is 0. The average value of the current in a steady state sinusoidal system is 0, which would mean the average power delivered to literally anything would always be 0. It's not. The average power is actually 1/2 the magnitude of the current times the magnitude of the voltage. Because of the trig identity, it's the exact same thing that we're using here, right? So when we multiply two sinusoids together, we're always going to wind up getting a DC offset just based on those trig identities. Okay. And I guess I should have graphed that on Desmos instead of relying on me to draw it shittily. That's what computers are for. All right. So we are going to look at a Z-axis gyroscope. So very similar to what I drew the other day. We're going to have a proof mass here in the middle. These are my drive mode springs. That are anchored. So I have this support structure right here. I'm going to have a comb drive actuator on either side of this guy. So this bit right here represents one of my drive electrodes, and then I've got another set of drive electrodes over here so that I can push it in both directions. So this is my drive structure. Now let's talk about my sense structure. So I'm gonna have springs over here. And over here that are allow me to, my structure to move in the vertical direction. Same thing on the bottom side. And then the real crux of my sense structure is going to be another comb drive. On the top. And a similar structure down here on the bottom. Like so. So my drive mode direction, XD, is going to occur in this direction, and my sense mode displacement, XS, is going to occur in this direction due to rotations about the Z-axis. So let's give us some parameters to work with here. This is going to be an extensive list of things. So the mass of our drive mode will be 5 nanokilograms. The mass of our sense mode will be 6 nanokilograms. The reason why we have different masses for this structure is in the drive mode, we're just moving this central mass, but in the sense mode, we're also moving this bit up here and this bit up here, which are going to contribute to the mass that the sense mode sees, right? Under the assumption that the springs are effectively negligible. The total spring constant for the drive mode, 0.8 newtons per meter. The total spring constant for the sense mode, 3.8 newtons per meter. The total number of fingers for our drive mode comb drive, so this is going to be 100 per drive. And then we have, I think I just did 20 fingers in total for the sense mode. Our quality factor for the drive mode is 50. Quality factor for the sense mode is also 50, quite low. Now let's talk about other critical dimensions here. So for the comb drive, for our drive mode, the fingers have a height of 5 microns, a length of overlap starting at 20 microns, and a nominal gap of 2 microns. And then for our sense mode comb drive, we have a height of 5 microns, a nominal gap of 50 microns, excuse me, a length of overlap of 50 microns, and a nominal gap of 2 microns as well. Let's see what else you guys need to know. We're biasing this thing, so our central structure has a bias voltage of 15 volts. And then we're going to use an AC drive voltage on our drive electrodes here and here of 1.5 volts to induce our movement. And our goal for this monstrous thing is to calculate the maximum change in capacitance experienced by the sense electrodes due to an angular rotation of omega is equal to 50 radians per second, which is extraordinarily fast. We're spinning the hell out of this stuff. All right, so we know that our capacitance in our sense system is going to depend on the displacement that we experience in our sense direction, right? So effectively, our sense mode is a transverse comb drive, where these electrodes, let me put a red arrow here. These are the ones that I'm talking about, are going to move either closer to or further away from the stationary electrodes here, depending on what the amplitude of the sense vibration is, right? The sense vibration in turn depends on the Coriolis force, and the Coriolis force experienced in turn depends on the drive mode vibration. So that's where we're going to start. We need to figure out what our drive mode vibration is. So our drive mode vibration, we're assuming that we're going to operate this thing at the resonant frequency, mechanical resonant frequency of our drive mode. So we know that XD should be approximately -J QD over KD times, I'm putting in here the magnitude of our AC force, because that's going to be our maximum displacement that we see. All right. So what's the maximum value of our AC force going to be, right? So if we go back here, this is the situation that we have. We have a DC voltage and then an AC voltage superimposed on top. So we're going to use this particular equation where we're going to have to figure out what DC by dx is. I'm going to double this force because we have 2 drive actuators. So this is 2 VDC VAC. And then it was everything else, derivative of, yeah, DC by dx. So what's that DC by dx term going to look like for a longitudinal comb drive? So the capacitance of a longitudinal comb drive is, trying to remember, it's 1N or 2N. Let's just say N epsilon, then my force is twice as small as it needs to be because I forgot to include that second factor of 2 in my math, but okay, we'll get to there. So N times H times L plus X over D, and then there's two capacitances for every overlap, one to the left and one to the right. So that's going to make that twice as long, which is just going to make everything else scale by that same factor of 2. So that's not going to be too bad of a deal. So if we were to take the derivative of this thing with respect to X, that's just going to give us, let's call it 4 now, VDC, VAC, N epsilon naught, because our permittivity is air, times the drive height divided by the drive gap. Does that make sense? Okay. And so if we were to plug numbers into this particular thing, what we would wind up getting is exactly twice 99.608 nanonewtons. So let's call it approximately 200 nanonewtons because I'm too lazy to figure out what that math is. So our force, pretty small, which is what we would expect for a capacitive comb drive. We wanted to increase the magnitude of our force. We need more fingers, we need a smaller gap, we need more area, or we need larger voltages, right? Plugging in this value here, we wind up getting a displacement that is going to be negative J, so let's see, 6.225 times 2 is going to be 12.450. Microns. Okay. Where the factor of negative J simply means that our displacement lags the application of our force by 90 degrees. So that's that 12.450 microns is effectively the maximum displacement that we would see as we oscillate back and forth. Okay. So we figured out what our drive mode displacement is. We could figure out what our Coriolis force is, but I'm not going to because we developed an equation for the sense mode frequency response where we had already substituted that result in. So what we need to figure out now is this a matched mode resonator or a matched mode gyroscope, a separated mode gyroscope, or potentially neither? And in this case, it's going to turn out to be neither, and we'll talk about that in a moment. So omega D is simply the square root of KD over MD, which comes out to be 12.649 kiloradians per second. Omega naught D, simply KS over MS. Omega naught S, thank you. Comes out to be, where do I have this written down? 25.166 kiloradians per second. So the modes are very much not matched. Omega naught S is definitely larger than omega naught D, but I don't know that I would call it significantly larger, right? Right. So I solved this thing using MathCAD to get my transfer, or not my transfer function, my displacement. And then I also looked at what the approximate values would be if we were using separated modes. And they are pretty similar, but I want to go through it here, right? So because I can't gut reaction say omega naught S is significantly larger than omega naught D, I evaluated XS using the following expression. -1 over MS, and this is just what we derived the other day. And I get, so twice MD XD capital omega. Our operating frequency here is omega naught D, so we have omega naught D squared times omega naught S over QS divided by omega naught squared, omega naught S squared minus omega naught D squared plus omega naught D omega naught S over QS quantity squared minus J twice MD XD capital omega naught D omega naught S squared minus omega naught D squared. All of that is divided by that same denominator, omega naught S squared minus omega naught D squared plus omega naught D omega naught S over QS quantity squared. And putting this again into MathCAD, I got 13.86. Actually, this should be twice this large, because you know what? Let's make sure I'm not screwing something up here. Let's just look at the damn MathCAD sheet. All right. So the changes that we are making is I'm putting a 4 here because I didn't do the derivative correctly. And then everything else should propagate through. So we said 12.45, or that's the wrong thing. Displacement of 12.45 microns, all that seems legit. So I now get a sense mode displacement of 27.726, which is twice the 13.863 that I got before. Makes sense. Just wanted to double check things. Uh, 27.8 angle 0.771 degrees nanometers. So in a perfect world, right, we would see that our sense mode displacement and our drive mode displacement are exactly 90 degrees out of phase, and we're really close. Okay, so things are looking pretty good there. Just bringing back that MathCAD sheet really quickly. So if we estimated and said, you know what, omega naught S and omega naught D are close enough, let's call them matched. The displacement that we get using that matched mode equation was 2.0 microns, which is actually larger than the gap that we're trying to transverse or whatever. Obviously not valid. Using our more exact method of just using the entire transfer function and everything, our displacement is 27 nanometers. I'm going to scroll down here. When we look at our sense mode approximation, 20.7 nanometers. So we're much closer to being a separated mode system than we are to a matched mode system, even though our sense mode resonant frequency is only effectively twice our drive mode resonant frequency, right? So anyway, so even though those resonant frequencies are relatively close together, we could have gotten a arguably similar result just by saying this looked like a separated mode. So I would argue that we don't even need full orders of magnitude of difference. If one is 5 times larger, that should be good enough to be using that separated mode approximation. All right, so from there, remember what screen I'm looking at. So this is the magnitude of our sense mode oscillations. So this is what's going to cause our change in capacitance, right? So at no Coriolis force effectively. So when we don't have any sense mode vibrations, the capacitance of our lateral comb drive is going to be twice NS times epsilon naught HS LS over DS, which comes out to be 44.271 femtofarads. And then our capacitance with the application of our Coriolis force is going to come out to be NS times epsilon naught HS LS over, excuse me, that's not right, times 1 over ds plus the magnitude of excess plus 1 over ds minus the magnitude of excess. And this is going to change appreciably from what I had because of the nonlinear relationship between capacitance and that displacement. So I'm going to look at what my MathCAD sheet has here. Just scrolling down. 44.279 femtofarads. And so our change in capacitance is approximately 8 attofarads for this system, 10 to the negative 18 farads. Okay. That's an incredibly small change in capacitance because we're getting an incredibly small displacement in our sense mode. So what can we do to increase the sensitivity of this device? There's a couple of very obvious things. I'm going to scroll up here to our parameters. Yeah, that's the biggest one. Making it way more fingers. 20 fingers is an incredibly small amount of fingers to use for any type of capacitance sensing. We could also increase the number of fingers in our drive, if at all possible, to induce a larger displacement using the same voltages, which would in turn give us a larger sense mode displacement as well. So the biggest change that we could make would be to cram more fingers on this thing, if at all possible. What's something else that we could do? Q of 50 is absolutely terrible. You're right. So if we were able to design this thing to have a significantly better quality factor, even 1 order of magnitude better would get a significantly larger response out of this system. What's something else that's kind of obvious here?
Main mission voltage, that seems like 50 volts is a little bit low.
So we could get a larger displacement or a larger force, which would propagate through. That's absolutely true. What I'm looking at here is a spring constant Ks that's, over 4 times larger than the spring constant Kd. If we were able to bring that spring constant down, so if the spring constant of our sense mode is softer, we're going to get a larger vibration, which will give us a larger change in capacitance, right? So there are a lot of things here that could be optimized to get us a significantly larger displacement, a larger measurable signal. Okay, so, but that's us going through a gyroscope in full. So expect your take-home problem to be something similar to this, but I'm going to try to make sure that you get to use one of the approximations and don't have to suffer through using MathCAD or Wolfram or whatever you choose to do to make everything work. I don't care for it either. I love MathCAD because I'm used to using MathCAD. I like. Yeah, no, I like math symbolically and then use the computer to put numbers in. I don't like to use the computer to do the symbolic stuff, but anyway. All right, so we have analyzed the behavior of a gyroscope from tip to tail, starting with the input side of causing vibrations and seeing what our change in output signal or change in capacitance is going to be. So the last little topic that I want to talk about is quadrature error. This is going to be very brief. So ideally, the sense and drive mode vibrations in a gyroscope are perfectly orthogonal. And without a Coriolis force present, the sense mode is not excited. So I'm going to draw a dumb little picture here to try to explain what I mean by this. Okay. So these fingers here are representing portion of a comb drive actuator. And then this central structure right here represents a portion of the mass, right? So effectively, without Coriolis force and our quadrature error term is equal to 0, we should see perfect up and down vibrations. If we had a Coriolis force present, so this is going to be with Coriolis, and our quadrature error term is equal to 0. What is the path of the mass going to look like? You guys have any thoughts? Elliptical. Yeah, so it's going to have movement in both the X and the Y direction. So we're going to have some sort of elliptical movement. Okay. So now let's revisit our first picture. I'm not going to try to draw what happens when we have quadrature error and a Coriolis force because it's just going to be a wonky looking thing. So this is what the effects of quadrature error will do. Okay. So let me explain more what quadrature error is. Okay. So quadrature error represents a mechanical coupling between the drive mode vibrations and the sense mode vibrations caused by manufacturing error for the most part, right? So if one of our springs isn't exactly as stiff as the other springs in our system, and so this is going to be without Coriolis, and quadrature error term is going to be not 0. What we're going to have is instead of perfectly vertical motion, we're going to have slightly skewed vertical motion that has some horizontal component. Excitation in our sense mode without the presence of a Coriolis force, right? Which is problematic for when we're trying to measure the Coriolis force, which we have seen is incredibly small. So if we are inducing vibration in the sense mode that isn't from the Coriolis force, then we have to figure out, well, then how do we decouple that, the Coriolis force vibration, which is in the horizontal direction in this case, from that quadrature error vibration? And the short answer is it's incredibly difficult and requires a lot of signal processing to do that. So other ways to reduce quadrature error are to physically trim at your springs to make sure that they are exactly the same, which is overwhelmingly expensive. It's done in quartz crystal resonators a lot, or piezoelectric resonators, because you have a bulk mode resonator. You just have a chunk of crystal and you're exciting it to vibrate by rapidly applying and taking off the voltage, right? You don't have springs and all of that kind of stuff to really deal with. So you just have to make sure that your crystal is of a nice shape and you're good to go. For a silicon based gyroscope, it's not really cost effective to do that. And the processing involved would be incredibly difficult. So what is done instead is what's called electrical trimming. And electrical trimming isn't actually trimming anything. It is simply using slightly different bias voltages to make the spring constants balance each other out. So we would have a situation like this, right? So here is our resonator, and to get rid of that coupling between the drive, might put VDC minus some small delta V in opposite corners here and here, and VDC plus some small delta V in opposite corners here and here. So we're effectively using an electrostatic spring by making those voltages slightly offset to confine the vibration to a single direction. All right, so that's all I want to talk about for quadrature error. And that wraps things up. I'm going to work on all those video lectures, so you guys got first dibs. I'm putting the video lecture, I'm hoping to get all of the video lectures for this class up this afternoon while I lock myself in my office. I do have a meeting at 2:30, but that shouldn't last more than a half an hour or so.
It brings a lot of information there, a lot of very.
Yeah. I'm gonna get these videos posted so that you guys can have the next 2 days to make out everything and study for your in class and all that kind of stuff on Friday. So yeah, I very much understand that I need to get the videos up today in order for you guys to have enough time to synthesize things, go back, make notes, figure out how to answer all those 12 questions or whatever I have. So that's my goal. By 5:00 p.m. I hope to have the overwhelming majority of the videos that are missing uploaded. Yes. Well, I mean, it's hard to describe what it's gonna be, but think like random orbital sander.
Yeah.
Yeah.
It depends on which one's down.
Yes. Yeah, so typically speaking, that epsilon Q term is very, very small. Like we would expect only, probably less than 1% of the vibrational energy in the drive mode to be transferred to the sense mode. So it's going to be small, but as we saw, the displacement in the sense mode can also be incredibly small, in the order of nanometers and things like that, unless we design very well. So quadrature error is a huge thing. It's why gyroscopes are probably the most complicated MEMS device you can design. Yes. Well, they were. Yeah.
Comparison to like a simple.
For sure, yes. Like applications where quadrature error doesn't matter is like the Wii controllers and stuff like that, where it's just like, you're going to be swinging the hell out of this thing. But then if you think about something, so like where are gyroscopes used in our everyday lives? I mean, we have multiple gyroscopes in our phone. What are the gyroscopes in our phone used for?
One that they're used a lot for stabilization.
So I was expecting you guys to say, oh, the screen knowing when to change. But the camera stabilization is the key thing here. So what do you think the rotational speed of your hands when you're trying to take a picture is?
Probably not zero.
For most people, it's on the order of, radians per minute of angular change. Right? So we did something there with 50 radians per second change and saw that we were getting nanometers of displacement. Right? So granted, that particular gyroscope was designed poorly because it should have had a lot more fingers to measure things and all that kind of good stuff. But if you need to measure a very, very slow rotation like that for image stabilization, you need extraordinarily high sensitivity, which means your quadrature error term has to be effectively zero for you to actually get anything useful out of your sensor.
So this is their second is for precision devices, you have a safety component for. So when you run this one, you actually.
Okay, yeah.
This is like.
I would think so. Like, I'm not super familiar with that term, but it would make sense to me. You effectively want to make sure that it's reaching some form of steady state before you do whatever it is you're going to do with it. So that any transients have died out, whatever those transients might be.
I think I'm
Right. All righty, anything else before I go lock myself in my office and edit videos?
You're telling me the reason I suck at Wii Sports is because they put qubits all around. Not physical ability.
Let's go with that, yes. What's amazing actually is that the Nintendo Wii actually drove a ton of advancement in in gyroscope design
What's really cool.
and really MEMS gyroscope adaptation or adoption, sorry.
The Wii, which with the user in the some environment business center, where Microsoft, because it's the Kinect.
Mhm.
The Kinect is not used anymore for video game stuff. What it is used for is for image tracking. And advanced image tracking significantly. Just like the maker community.
Mhm.
And so,
Yeah.
there's like OpenCV is a computer vision and stuff like that. That wildly popular. And it basically wouldn't exist today if the Nintendo Wii didn't exist.
That's super neat.
So video games make the world go round.
They do, absolutely.
Heck yeah.
All right, for all you guys on Zoom, thank you for bearing with me and all this kind of jazz. And like I said, I'll get these lecture videos up as soon as I possibly can so that you guys can study. I'll see most of you on Friday for your exam.